talk about space, and in the space community, we've talked a lot about the value of international cooperation. We've talked about it here in the context of debris mitigation and other things. This week, you've been in the news because of questions about a darker aspect of international relations. I wonder if you'd like to address that first, and then we can go on.
Sure. I'm in the fund management business, and we invest in tech companies around the world. And some of our early investors, actually, a couple of our early investors were from Russia. It was around 2009. And some of the journalists, they believe that we should not have taken money from those investors in 2009. But what they fail to appreciate is that the international relations between US and Russia were very different at the time. And I remember Secretary Clinton came to Moscow and she pushed this reset button, if you remember that.
Yeah.
There was a lot of excitement at the time, and a lot of capital went into Russia from US, and some of this capital also went in the opposite direction. And we have returned money to those investors around 2014. And that, from my standpoint, that's the end of the story. But in general, when I was growing up in Soviet Union behind the Iron Curtain, my father always told me that I should try to stay away from politics, and I tried to follow his advice since then. And people who know me well, they know that my real passion is technology, science, and space. And that's what I prefer to focus on.
Was it your mother or your father who chose to name you after Yuri Gagarin?
I think it was a joint decision in 1961.
Good year for it. So the communication technology we'd like to talk about first. We've been talking about communication from space to the Earth, communication around space. You're looking about a much deeper space communication project. I was there when you launched this, about 2 years ago now. So tell us a little bit about Breakthrough Listen.
Well, I would like to make a step back and share with you sort of the philosophy of everything that I'm doing in the area of space. The one overreaching question that we're asking at our Breakthrough Foundation is, are we alone in the universe, or can we find life in the universe? So this is really the essence of everything that we do.
And we've heard a little bit about Arthur Clarke today, but I think one thing that's very relevant is I think it was Arthur C. Clarke who first pointed out that that's a question which has an amazing answer, whatever the answer is.
Right. If we are not alone, obviously it's probably one of the biggest discoveries ever. And if it will be increasingly likely over many years of observations that we are alone, then it means that we need to kind of put our act together here on our planet.
So, having said that the overall focus is life in the universe, I think the first of the actual projects you started was the LISTEN project, yeah?
Yes. So this is really an attempt to find a extraterrestrial civilization through scientific observations in radio spectrum and also in optical spectrum. And we have been doing this for about 2 years now. In radio spectrum area, we work with a number of largest telescopes in the world. The first one we launched was Green Bank Observatory in US. The second was Parkes Observatory in Australia. And we are also in conversations with the so-called SKA telescope, Square Kilometre Array, which is based in South Africa and Australia. And then we also signed a memorandum of understanding with the largest Chinese telescope called FAST.
That's far more telescope time than has ever been given to SETI before.
Right. So SETI is Search for Extraterrestrial Intelligence, and this is the essence of this project. So while looking for a possible signal from a developed civilization that would be developed enough to have radio capabilities, as well as optical, laser capabilities. And we are looking at a much broader spectrum than ever before, as well as because of the progress in hardware and software, we can now analyze and process those signals much faster. So overall, on any given day of observations, we see as much as any previous search in a year, roughly speaking.
Right. And is that continuing to accelerate?
Yes. So we have covered so far, we have almost completed a survey of 2,000 nearby stars between sort of a few light years and 150 light years. And the publication is coming to reflect that. So in the 2 years of observations, we have found about 11 suspicious signals, but they've all been ruled out with more sort of careful observations.
What's your protocol if you don't rule something out?
Well, the protocol is basically to go and check again a few times, and then share this information with scientific community so that they can also check it. The example of this cooperation is actually around the so-called FRBs. Mm-hmm. This stands for fast radio bursts. And in looking for those narrow band signals from extraterrestrial civilization, we actually found something we have not been looking for, which is radio signals from those mysterious objects that are called FRBs. And those objects are located 3 billion light years away from us. And we have been able to identify characteristics of those objects that were not clear from previous observations.
It's a wonderful example of the fact that, if you look in a new domain, a new time domain or a new frequency domain, you quite often find something completely different, like the original discovery of gamma ray bursts from looking for nuclear tests.
Yes, exactly. So, but the interesting thing is that we don't really have one consensus explanation of the nature of those sources of radio signals. Just to give you the perspective on this, in 10 microseconds, they emit as much energy as our sun in a year. So it's a very powerful source of energy. And the best explanation we have is that those are neutron stars interacting with black holes. But some speculative explanations are also related to extraterrestrial civilization.
Oh, speculate away.
Well, the minority of experts, but of course, more likely is a natural explanation for this.
Okay, but you mentioned that the part of Breakthrough Listen that looks for messages from lasers is at the Lick Observatory. But of course, you're also, in the more recent part of Breakthrough's work, you're looking at a big laser of your own, the sort of laser that you might actually see across intergalactic, intergalactic distances. Right. You could see such a laser, yeah? What do you want a 100-gigawatt laser for?
Well, this is another project that we are beginning to fund, and this is called Starshot. And this is the first sort of practical attempt to develop an interstellar mission, but very different from anything that people were really thinking about, because it's a very small spaceship, about a few gram mass and small size, but the one that you can push with the photon engine, which sits on the ground. And with enough luck and energy, you can accelerate it to about 20% of speed of light. And with that type of speed, this small spaceship can reach the nearest star in about 20 years. So we have identified, so we announced this project about a year ago together with Stephen Hawking. And recently he really likes to talk about this as sort of one of the ways out for our civilization to survive. And the combination of technological advances in the last 10 years actually allows us to practically approach this. And we're focusing on 3 areas mostly. One is the photon engine itself. And we have launched the request for proposals from academic community and engineering community. And we have received a few dozen proposals. We have selected about 10.
So this is in solid-state lasers, or?
Yes. Well, you need a lot of lasers, and you need to what is called phase lock them, so that they effectively create one big laser. So this is already practically funded initiative. And then the second one is called SAIL project. So we need to design a material that doesn't exist yet for the sail to be pushed by this beam of light from the ground. And then the third project that we will fund in 2018 is going to be a communication project on going into details on how can you communicate and send images back from Alpha Centauri at interstellar scale.
And we were hearing earlier when we were talking to Steve Jurvetson about the idea that one of the things about the rescoped version of the BFR that Elon Musk's now talking about, BFR, not FRB, is that it's useful from day one. Are there any sort of like near-term applications to things like a photon drive like that, or such a material?
Yes, there would be. If you build that scale of sort of engine on the ground that can push the sail and the object attached to the sail, then instead of going very fast and pushing something very small, you can choose to go slower but push a larger object. And it can allow you to move around the solar system also a bit faster, quite a bit faster.
What do you mean by quite a bit faster?
Probably an order of magnitude faster, maybe 2 orders of magnitude faster. So maybe you can reach Mars in a week, something like that.
For what sort of size payload?
Maybe kilograms, maybe dozens of kilograms. But so there are quite a few things that you can do in the solar system if you build something like this. But also, it is a good weapon against meteorites. So if obviously there's a meteorite threat for our planet, and with a laser of that scale, if you can build it, then it can be quite a good protection from some of the meteorites. If you really shoot with high precision, you can hit one side of it, and it will deflect the trajectory.
How meteorite orbits change naturally.
Yes.
Who would you want to give control over such power to?
Well, this machine can only be under international control. I mean, it cannot be controlled by any given private or even public entity. It should be a global international effort. First of all, to build it, because it's not going to be cheap. But second, there are some precedents of this. There is one facility called CERN, which was about $10 billion initiative, maybe a bit more, which is an international organization which includes probably about 25, 30 countries.
I think more than that.
Maybe more than that now. So we need something like this to obviously control that type of machine. But also we need not only control, but more like a consensus something like a consensus whether we should be sending those spaceships so fast and so far. Because it's sort of like a big deal if you send something to the nearby star.
And do you know which nearby star you're interested in?
Well, the one which is really practical is Alpha Centauri. It has 3 stars. And in fact, I think we've been very fortunate because an Earth-like planet was already discovered, which is orbiting one of those stars called Proxima b. And the star is in so-called habitable zone. And it means that it can have liquid water on the surface. So we basically already have a target. But 4 light years, if you move at 20% of speed of light, it takes 20 years to get there. If you take some more remote stars, then it takes more like 100 years to get there. And 100 years is a bit too long to have a serious conversation.
A little too long. But I understand that also so we've talked about breakthrough Starshot and breakthrough LISTEN. More near term is actually looking for some of the targets that you might go to. Tell me a little bit about that. That's the third leg of the tripod is breakthrough watch, yes?
Exactly, yes. So it's LISTEN, Starshot, and now watch. And the watch is something much more near term and practical, where we fund an upgrade of certain telescopes. One of them is VLT in Chile. And the idea is to make it so that after this upgrade, those telescopes can observe some nearby stars and be able to take direct images of the planets around those stars. And if you take direct image, there's a possibility to see maybe the atmosphere and the composition of the atmosphere and things like that, at least preliminary. And then another initiative that we're funding with Sydney University is to potentially develop a small-scale space-based telescope with the same goal, to be able to take some images of the planets that are orbiting nearby stars.
How far along is that part of the project?
Well, we're doing a feasibility study, but if it is possible, then it will probably take a few years.
So that would be something to actually take in. That wouldn't be like TESS, which is launching.
The VLT project, I think the observations might start in 2019. The space-based telescope will take a little longer. And if you're talking about LISTEN, it's a 10-year project. We're in the 2nd year of it right now. And the idea is to look at the million nearby stars in 10 years and a few hundred nearby galaxies in the same time frame. And as far as Starshot is concerned, the time frame may be something like 25, 30 years to develop this technology and build the machine. Again, if the feasibility study is, promising enough.
I think when you originally talked about it, you talked about there being 20 potential showstoppers.
Yes, but the 3 main ones are the ones that we are trying to solve right now. I think if we solve the 3 main ones, the rest will probably not be so serious anymore. So I think the feasibility study will probably take about 5 years. And then if we move it to the next stage, then it will probably be a 25, 30-year project to build and another 20 years to get there, another 4 years to get the signal back.
Adds up to a fair chunk of a lifetime. But we've talked here mostly about looking beyond the solar system. Is there any other form of looking for life in the universe that you might be more interested in within the solar system?
Yes. So we have identified, again, under the same umbrella of trying to find life, any kind of life in the universe. One way is to look at the signals that an intelligent civilization can be sending to us. This is LISTEN. WATCH is trying to identify some of the nearby planets that can be potentially habitable.
And so, just going back, would you ever imagine moving WATCH forward to actually look for signs of life on other planets?
Oh, yes.
Is that something that you would feel would come within sort of like the scope of a philanthropist like yourself, or is that something more at the sort of like CERN level?
Well, I think it's a cooperation. Like VLT was the telescope which was already built. We're just investing in some sort of upgrade to make it so that it can see those specific objects. I don't think it's ever a competition because the capital in this space is so scarce that nobody is really competing with anybody. I think everybody is looking for money to do something. So we are rarely in a competitive situation. Now, the Starshot, of course, is the very active attempt to go somewhere and have a look. But if you are talking about the ground-based and space-based telescopes, then in the next 10 years, probably there will be a dramatic progress in trying to identify whether there is some life on some of the nearby planets orbiting other stars through the composition of the atmosphere of those planets. So as soon as we have enough precision, then, like looking at the composition of our atmosphere, we would find out that it's in a disequilibrium that can only be explained by some organic life on the planet. So that's kind of the logic to look at the atmosphere of those planets.
And are you sure that the scope for progress in telescopes in the solar system isn't greater than, I mean, could you find yourself being able to learn more about those planets from back here than by sending a tiny little wisp past them?
Not really. If you are able to go there, it's always more interesting to go there because the telescopes of comparable sensitivity would be probably a few hundred kilometers, and in space. I mean, you need to put it in space, and those would be very expensive pieces of equipment to assemble in space. But I'm not saying that one replaces the other. I think eventually we will probably be capable of doing this. And if there is a civilization which is even 1,000 years more advanced than ours, and 1,000 years is a very small fraction of the time that our universe exists, then they would probably be able to build those telescopes, and they would probably know already now that we exist. Because for about maybe even already 3 billion years, we have organic process on our planet. And it's enough time for this information to spread, billion light years out. So if somebody had a decent equipment 1 billion years ago, they would know that something interesting is taking place on this planet.
No, I just like the very idea that there's an issue where building a 0.2C Starship is the cheaper alternative to just building the telescope.
It is actually a cheaper alternative, only if you're talking about nearby stars, right? I mean, if you think about going across the galaxy, then
well, if we're only going to talk about nearby stars, Yuri. But actually, let's come a bit nearer, because I know that you're also interested in, I mean, there are various places other than the Earth in the solar system where one might look for life. And you're interested in perhaps exploring some of those?
Yes, but just I thought about something else interesting that you might be interested to hear is that when we talk about Breakthrough Listen and that this new emerging telescope which is being built called Square Kilometre Array in South Africa and Australia, once we build this machine, for the first time, we will be able to try to see the leakage of any civilization. Leakage meaning that, like our civilization is leaking because we're using radio and we're using radars and things like that. So we're basically sending signals already, not deliberately targeting any other civilization, but just sort of general leakage. So for the first time with SKA, we'll be able to see the leakage from nearby stars. So even if somebody not deliberately targeting us, we will be able to see those signals.
It's interesting. I think there's a feeling out there among people who've looked at it a little bit that there's a feeling that we can already do that, but we really can't. To some extent,
No.
SETI is much less advanced than people tend to think.
Right. So with that type of equipment, this is the first time we'll be able to see leakage from probably up to 10 light years away from our planet. So, and it gives us probably a handful of stars. So not much, but it's a good thing to know. And then going back to our solar system, there are, of course, a few candidates in our solar system to have some form of life, not intelligent life as we already know, but some form of life, maybe microbial life, maybe something more serious. And in the last few years...
You obviously haven't been ill recently. Microbial life can be very serious.
I know. So the consensus among the experts in astrobiology is that there are probably three main candidates. One would be Mars, underneath the surface, not on the surface, but probably maybe a meter below the surface. But then you need to send something to Mars and drill sort of pretty deep. And we cannot do it with robots right now. We kind of almost need to send humans there.
Bruce Willis, I believe, yes.
Yes. And this is what Elon Musk, of course, is working on. Then the second candidate is Europa, which has a pretty thick ice and maybe 100-kilometer ice. And there are different ideas about how do we sort of drill the ice or blow up the ice or whatever, and go and try to reach the ocean underneath and see if something is swimming there. But the most promising recent candidate, probably the most promising, is Enceladus, one of the moons of Saturn. And it was just recently discovered that there are some promising organic signals coming out of the plume of Enceladus. So the good news about Enceladus is the plume. So
just to be clear to people who aren't chemists about this, organic here meaning complex molecules, not necessarily meaning life.
Yeah, exactly. But we already have seen that there are these big plumes that are always sort of shooting a couple 100 kilometers up. And we've already been able to go through the plume and see some early signs encouraging that would basically means that we should keep looking. And then there are different ideas floating around on how do we send a mission to Enceladus to basically do a more thorough investigation of the plume to see maybe there are some amino acids there or something of that nature that would be kind of a smoking gun for life below the ice of Enceladus. And what we have been thinking about recently, so we formed a sort of a little workshop around this idea. Can we design a low-cost, privately funded mission to Enceladus, which can be launched relatively soon, and that can look more thoroughly at those plumes to try to see what's going on there, ahead of a more expensive mission that NASA is considering right now, which might take, maybe 10 years to launch. And,
when you say look at, do you mean remote sensing or actually flying through the plumes?
Flying through the plumes, yes.
So it would orbit Saturn and come through the plumes of Enceladus, or would orbit Enceladus itself?
the simplest way is just to fly by. If you want to slow down, you need to make a few rounds around Saturn. This will take maybe a couple more years to do. But all options we're looking at right now. How can we, for the first time ever, design and send and launch, actually, a privately funded interplanetary science mission? So that's what we're thinking about.
Well, that's one we started off today. I see we're out of time. We started off today hearing from Carolyn Porco about the Cassini mission, and she ended up by showing us, penultimately she showed us the plumes of Enceladus, and then at the end she showed us very movingly the site of the Earth seen from Saturn, and this idea of seeing one living planet and exploring the possibility of another living moon. It's very exciting to know that you're thinking about taking that vision further. Thank you very much, Yuri.
Thank you.